Hello, this is a video on analytical chemistry. I'm going to talk through all the different aspects of it, going from combined all the way through to the triple only content. So first of all, we're going to start off with pure substances. So we need to understand how, because analytical is all about looking at how we can tell different things apart, how we can test different substances to understand if they're pure, impure, what they contain, etc., etc. So pure substances, we need to look at our melting and our boiling points. These are good indications of if a substance is pure or not. Now, let's say we have pure water, although H2O to start with. We know the boiling point of water is 100 degrees centigrade. Now, if it's impure, we will have a range of melting point varying, let's say, between 95 to 105 degrees centigrade. It's very similar to this, but it's not exact. Therefore, we know it will be impure. And we can see this in graphs. So this is temperature, and this is time. So for a pure substance, and I'll do pure in red, it will go up, the temperature will go up, and then it will hit the boiling point, and it will flatline. And then once it's changed state, so it's gone into a gas, the temperature will go back up again. And this flat line is what we're looking for a pure substance. Now, if we do it with an impure substance, it will look like the following. The axes are still the same, but this time it will go up. Then it'll hit that boiling point, so it will change. Instead of being flat, it will still be an incline, just slightly different gradient. So this is not flat, flat. So the flat line indicates pure. So flat line on graph equals pure. And that is how we can use boiling point and melting points to tell if something is pure or impure. Flat line, we have a pure substance. A slight gradient on it means an impure substance. Right, next we'll move on to formulations. So just clear this out. So, a formulation. Now this is a substance in which every chemical involved has been measured out precisely plus accurately. So we need to make sure every single chemical in there has the exact amount. If we do too much of one, it won't make the right formulation. Now some good examples of this are fuels, such as petrol. It's not just one thing, petrol, it's got other things in it as well. Cleaning products. If you get one of the quantities wrong in it, you won't clean as well. And a good example, which I'm going to go into a bit more detail, is medicines. So you can go to a store once you're 16, and you can buy something like ibuprofen or paracetamol. Now, on their own, you can get them as pure products, but sometimes you will see that more expensive ones containing things like caffeine. Now, the caffeine makes it a formulation because the caffeine has a different role. Sometimes contain caffeine. Now, everything involved in a formulation has a purpose. So, for this example, in medicine, ibuprofen is the painkiller part. It will kill the pain in the body, helping you to function. And then sometimes they contain caffeine. Caffeine speeds up pain relief. So it just speeds up a little bit, not by a lot, but a small amount. Now, if we put too much caffeine in, we'll end up having too much of the speed up, but not enough of the actual pain relief. If you have too much ibuprofen, we'll have a good amount of pain relief, but we won't have enough of the speeding up part. So that's what a formulation is. It's a precise and accurate amount of different substance or different chemicals in the formulation, plus each one has a clear job. Each chemical has a clear job. So that's what a formulation is. Right, next we're going to move on to chromatography. Now chromatography is a required practical in this topic, but you probably have done chromatography quite a lot. If not, I heavily recommend going on to BBC Bite Size. They have some excellent information regarding practicals. So, chromatography. Now this is a method of separating. Now, often the one that we will look at is paper chromatography, and that will be the one where you have the beaker, and you have a little bit of water down the bottom, and you'll have the bit of paper just touching the bottom of the water. Now on that paper you have that line, and on the line we put an ink dot. And you'll notice as time goes on, water will go up with the paper and it will take the dot with it. Now depending how far the ink travels depends on how soluble it is in water. So the more soluble, and by soluble I mean how easily it dissolves into water, the more soluble equals further distance ink travels. So if the ink travels all the way to the top, we have very soluble in water. If it only travels a little bit, it's not very soluble. And from this we can get something called an RF value. And that is our retention factor. And by retention factor, it's just how good it is at going up. So to get this, we would have to measure the distance from the line to the top of the paper, line to top of paper, and we'll need distance ink travelled. I'm using ink in this example because in paper chromatography, ink is what we will focus on. Other chromatographies will use different, but for this it's fine. So once we get these two, we can then do a bit of maths behind it. Okay, so the maths involved is distance travelled by ink divided by distance travelled by the water. For this example, in another example we could use solute and solution. We could put substance and solvent. There's multiple different ones that we can use in this example. So distance travelled by ink, distance travelled by water. Once you get that, you'll get our RF value, and that number has to be between 0 and 1. It can't be higher than 1, it can't be lower than 0. 0 means that it is not soluble at all, it didn't travel at all, and 1, it travelled all the way to the top, so it's the most soluble it can be. Right, so that is chromatography. Now we need to talk a little bit about different tests for gases. So we've got several different gases we need to know for. We've got hydrogen, oxygen, carbon dioxide, and we've got halides. Chlorine is the example we're going to talk about. Now, hydrogen, we got the squeaky pot test. If you put a lit splint into some hydrogen, it will make a popping noise that sounds a bit squeaky. So we listen for that, and that's what we have. O2, it will relight a recently extinguished splint. So the splint has just been blown out, it's still you've got embers there, you put it into oxygen and it will relight. CO2, we bubble through lime water. Now what you should notice as you bubble through the lime water is you will see it will go cloudy. Now you might have done this with a test tube, some lime water at the bottom and a straw. And as you blew through, because we know that we have carbon dioxide that comes out of us, you will notice that it will go cloudy, proving that lime water tests for carbon dioxide. And finally, we're going to talk about chlorine. So chlorine, we need to use litmus paper. Litmus paper. And we must be damp. And if it bleaches it, chlorine is present. So bleaches means goes white. Oh, goes white. So if we put chlorine gas nearby some damp litmus paper, it will bleach the paper, it will go white, and that shows the presence of chlorine. Right, that is all the content required for combined. Now the next bit of the video I'm going to be talking about is triple. Right, first of all we've got flame tests. Now this is an important step and we can use to identify metal ions. And so often they're in solutions in a salt. So we have something like sodium chloride or copper chloride, copper sulfate, and you'll notice this will work. Now what will happen is you will dip the dipstick into some of the solution and you'll pass it through a Bunsen burner. And as you pass it through, the Bunsen burner, the flame will change colour. Now you do need to know some colours, and I'm going to show you those. You see here, lithium goes crimson, sodium goes yellow, potassium makes the flame lilac, calcium makes it an orangey red, and copper 2+ makes it green. So these ones you do need to know for your exams. So, again to repeat, you pass the dipping stick or the splint that's got a bit of the solution on through the flame, and you'll notice that the flame will change colour. And depending on the change of colour, depends on the ion present. So that's the flame tests. Then we have metal hydroxides. So again, I've got some information that we can talk about with this. If we look, we form a precipitate, and depending on the metal that's present, depends on the colour of the precipitate. Now we do have a problem here. We have aluminium, calcium, magnesium all being white. Now the only one, when we keep adding the solution, is aluminium will actually redissolve and you'll get rid of the precipitate. So that's a key one. Now the difference between calcium and magnesium, that's where we come in a bit later. But for copper, iron and iron 3+, they've got very unique colours which are useful in this example. So that is metal hydroxides. Next we've got halides. Again, halides, I've got some information for that one. So halides, we use silver nitrate as a part of our test for this. Now, white will mean we've got chloride present, cream means we've got bromide present, and yellow, iodide. So as we go down the periodic table from the top of group 7 to the lower part of group 7, it goes down from white, cream to yellow. So we get this kind of spectrum of shading. So that will be silver nitrate. Right, and that's some of the key ones to test for. I'm going to make sure that there is a file attached to this video that has a lot more information on which you can go through. There's not a lot for me to talk about with this, it's just learning the tests. Now, there is a required practical for this. And in this required practical, you're given unknown salts, and you've got to figure them out by doing the tests. So you'll carry out the tests. Sometimes you might have to dissolve the salt to make a solution. So in the example of flame test, you want them as a solution. It works a lot better. And you must make sure you talk about recording observations. Often in the exams, they will give you, they want an answer. They want you to figure out what is the unknown salt. So they'll give you a bit of information about it, and then they say, how would you do this? Carry out the test, and then they'll ask you for the result. They will give you the information regarding that. So be mindful of that, but the required practical is just literally understanding every single different test that we have talked about. As I said, the sheet I will attach to this will have a lot more information in. Now there are two other things we've got to quickly talk about, and that is instrumental methods and flame emission spectroscopy. So, instrumental methods versus lab methods, effectively. So what you're doing in all of the practicals you would have done will be different to what they will do in an actual university style lab. They'll do what we call instrumental methods. Now these are accurate plus precise. However, they are expensive. And that's some of the key differences between instrumental methods and lab methods. These are easy to set up. Also, they are subjective. So let's say in flame tests, sometimes you get with a lot of flames a very similar color given off. Now, that means you're using the human eye to understand the difference. Whereas in instrumental methods, you're using a computer, and a computer can tell a lot more tiny differences between things. So, subjective is used, whereas these will use computers to analyze data. These are easy to set up / cheap. Cheaper, I would say. Not all of them are that cheap, but these are very expensive, some machines. So you just need to understand the differences between the pros and cons. And finally, we've got flame emission spectroscopy. And this is an instrumental method. Emission spectroscopy. So this is an instrumental method used often to tell what substances are present. Now, every single element emits their own wavelength of light, and you will be given different emissions, and you've just got to compare them to what data given. I'll try and find a question to go with this to look, but without looking at the question, there's not a lot to do, but it is all about matching up patterns. Let's see if we can find one. Something like this. And you get lines that match up, and that's the key part you need to do, is to look at lines matching up, because if the lines match up, it is present. So in this one up here, we've got some hydrogen present, as you can see here. We've got some helium present. We've got this one here, and we might even have some mercury present, because it lines up with this one at the top, and that's what you've got to be doing in your exam, is using that lining up. Right, so that is analytical chemistry in a nutshell. There's not a lot else to it, but I would make sure you learn all the different tests and the results for the tests, and I would make sure you understand how we go about doing things like chromatography and different flame tests. Thank you.